The indoor sound field is a problem of solving the wave equation in three-dimensional space and boundary conditions. Because of the complexity of room shape and interface acoustic properties, it is difficult to obtain a solution by mathematical physics. Therefore, the method of statistical processing was adopted. Due to the attenuation of sound energy during the propagation process, part of the sound energy will be absorbed when encountering the interface, making the sound energy from strong to weak. Therefore, in order to study the process of sound growth, stabilization and attenuation, it is necessary to combine the time and energy of sound waves, arriving at a certain receiving point, with the spatial distribution. The sound field is assumed to be completely diffuse, regardless of where the sound absorbing material, sound source, and receiving point are located. The diffuse sound field has the following characteristics. 1. The sound energy density is uniformly distributed in the room. That is, the sound energy density at any point in the room is equal. 2. The intensity of sound energy in all directions at any point in the room is equal. According to the assumption of diffuse sound field, the intensity of sound energy incident on any surface of the room per second is equal to 1/4 of the product of sound speed and sound energy density. The sound energy incident on all interior surface of the room is equal to the product of the sound energy intensity and the interior surface area. The sound energy absorbed by the inner surface per second is equal to the product of the intensity of the sound energy and the average sound absorption coefficient of the inner surface area and the inner surface. The amount of change in room sound energy is equal to the room volume multiplied by the rate of change of sound energy density with time. It is also equal to the sound power of the sound source minus the sound energy absorbed per second, which is the equation of indoor sound energy change. Among them, A is the amount of sound absorption, which is equal to the sound absorption coefficient multiplied by the sound absorption area. Assuming that the sound energy density is equal to 0, when T is equal to 0, solve the sound energy change equation to obtain the formula describing the sound growth in the room. It can be seen from this formula that, with the increase of time, the indoor sound energy density increases. When T tends to infinity, the indoor sound energy density reaches a maximum value, namely D0. At this time, the sound field reaches a steady state, and the sound energy radiated by the sound source per unit time is equal to the sound energy absorbed by the indoor surface. After the indoor sound field reaches a steady state, the sound source stops sounding. That is, when the time is equal to 0, the sound power is equal to 0, and the sound energy density is equal to D0. The sound energy change equation is solved to obtain the formula describing the indoor sound energy density attenuation. It can be seen from this formula that the indoor sound energy density decreases with the increase of time. The larger the indoor sound absorption, the faster the attenuation. The larger the room volume, the slower the attenuation. When the alternate takes the linear scale of the sound energy density, the attenuation curve is a negative exponential curve. It can be seen from the figure that, after the sound source soars, it grows rapidly and reaches a steady state soon. After it stops sounding, the attenuation is relatively slow. The indoor sound absorption affects the maximum indoor sound energy density and the decay duration. The smaller the sound absorption, the greater the sound energy density, and the longer the duration. And the opposite is the case when the sound absorption is large. When the alternate is in decibel scale, the attenuation curve is a straight line. Reverberation refers to the residual sound phenomena formed by the late reflection sound from various interfaces in the sound field after the sound source stops sounding. The reverberation time is used to characterize the length of this phenomenon. Sabin defined the time that the sound takes to decay by 60 decibel from the steady state sound pressure level as the reverberation time after the salt source stops salting. At present, the accepted definition of reverberation time refers to the time it takes for the salt energy density to decay by 60 decibel. There are three formulas for calculating the reverberation time. They are the Sabin formula, the Ealing formula, and the Ealing-Nathanson formula. Sabin's formula is based on a larger number of measurements and analyses to obtain the relationship between the reverberation time and the room parameters. Using the currently accepted definition of reverberation time, we write the attenuation rate expressed in decibel from the indoor salt energy density attenuation formula into the definition of reverberation time in decibel/s form, and the Sabin formula can also be obtained. As can be seen from Sabin's formula, the reverberation time depends only on the volume of the room and the amount of salt absorption. It can be seen that the salt energy in a large room decays slowly, and the reverberation time is longer. The more salt a room absorbs, the faster the salt energy decays. Since the Sabin formula is based on the assumption that the reflected salt energy decays continuously, and is based on the architectural form and the interior decoration at that time, it is only applicable to the case where the average indoor salt absorption coefficient is less than or equal to 0.2. According to Ealing, the salt will attenuate every time it collides with the interface, and the attenuation curve is typed. In order to calculate the number of reflections in a closed space per unit time, the concept of mean free path is introduced. The mean free path refers to the statistical average of the distance traveled by the reflected salt after one reflection from the inner surface to the next reflection. The mean free path of a conventionally shaped room is equal to 4 times the ratio of the room value to the internal surface area. Then the number of collisions between salt views and the indoor surface per unit time is equal to the speed of salt divided by the mean free path. Based on the assumption of the diffuse salt field, the indoor salt energy density and attenuation rate after unit time can be obtained, and substituting them into the definition formula of the reverberation time, that is the Ealing formula, is obtained. It is suitable for the case where the indoor average salt absorption coefficient is greater than 0.2. When the indoor average salt absorption coefficient is less than or equal to 0.2, the calculation result is close to the Sabin formula. Based on the Ealing formula, the Ealing-Nathanson formula takes into account the Earth's absorption of high-frequency salt at 2000 Hz and above. This absorption depends mainly on the relative humidity and temperature of the air. The salt absorption of air is equal to the product of the absorption coefficient and the volume of the room. The three calculation formulas of the reverberation time are based on fully diffused salt field and a complete space, but in fact the interface materials in each room are different. This makes the indoor salt absorption unevenly distributed, resulting in different attenuation speeds in all directions, and there may be more than one space, the attenuation rate different. Therefore, the attenuation curve on the decibel scale is theoretically a straight line, but in practice there will be a zigzag. The calculated value of the reverberation time will deviate from the actual value. Next, let's do an exercise. It is known that the room volume is 1000 cubic meter. The total indoor surface area is 700 square meter. The indoor temperature is 20 degrees Celsius. The relative humidity is 60%, and the average salt absorption coefficients of 125 Hz, 500 Hz, and 2000 Hz are 0.1, 0.25, and 0.3 respectively. Find the reverberation time of 125 Hz, 500 Hz, and 2000 Hz. The idea of solving the problem is further determine the calculation formula according to the numerical value of the salt absorption coefficient and frequency, and then calculate 125 Hz is a low frequency, and the salt absorption coefficient is 0.1, which is less than 0.2. Therefore, the reverberation time is calculated by using the Sabin formula to be equal to 2.3 seconds. 500 Hz is the intermediate frequency, and the sound absorption coefficient is 0.25. This is greater than 0.2. Therefore, the reverberation time is calculated by using Elin's formula to be equal to 0.8 seconds. 2000 Hz is a high frequency. Therefore, using the Elin-Knudsen formula to calculate, the erg absorption coefficient is found to be equal to 0.009, and the reverberation time is found to be equal to 0.6 seconds. You can try to calculate the reverberation time using Elin's formula for 125 Hz and see the difference between the two calculation results. You can also think about it. What is the appropriate reverberation time for each frequency band? How to use reverberation time for acoustic design? Can noise control take advantage of reverberation time? Should the reverberation time be the same for different types of rooms?